All right, today we're going to look at increasing and decreasing functions. Part of this is not calculus at all. It's actually a definition that doesn't involve any calculus. And then part of it is also, well, how do we find local maximums and local minimums? We already know how to find the absolute maximum or the absolute minimum on a closed interval for a continuous function. We identify the candidates by looking at the endpoints and at the critical points, and then we just test those. It's very mechanical, okay? Here we're going to have to be thinking a little bit more. So let's start. The definition of a function that's increasing on an interval is that for any two numbers, x1 and x2 in the interval, if x1 is less than x2, then f of x1 is going to be less than f of x2. That is the definition of an increasing function. In just a moment, we're going to learn some calculus that can be applied to that. And unfortunately, what students do is they start thinking that the calculus is the definition of increasing or decreasing. It is not. Okay, I actually had a fairly long argument with a teacher at the AP reading one year about this. And I'm like, no, you're wrong. Let me explain it to you in small words.
Did they concede?
No, but she was pretty stupid.
Oh.
So.
You didn't feel too bad about it?
And after a while, the table leader sat down with her and tried. I don't know that he got anywhere, but. And part of the problem is that this is increasing on an interval. It is not talking about a function increasing or decreasing at a point. We just about never talk about something increasing or decreasing at a particular point. It's always in an interval. Okay? And maybe that's part of what gets people as well. And then decreasing, if you have two numbers x1 and x2, then if x1 is less than x2, then f of x1 is greater than f of x2. All right, so, and we immediately follow that up with the calculus part. And again, I think this is why people conflate the two. The test for increasing and decreasing functions. If we let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Hey, what does that sound like?
The theorem.
The one we just did, which has a name.
The mean value theorem.
Thank you, the mean value theorem. It has the same conditions as the mean value theorem. You're going to find actually there's a fair number of things that we do that have the same conditions as the mean value theorem. So, if my derivative, f prime of x, is greater than 0 for all x in the open interval from a to b, so we don't care what happens at a, nor do we care what happens at b, then f is increasing on the closed interval from a to b. Okay, remember increasing is on an interval. So some people will go, well, what if it's not increasing at a? I don't care. Okay, we're saying on this interval, this function is increasing, not at a or at b. I hope I've made that clear. So if f prime of x is less than 0 for all x in the open interval from a to b, then f is decreasing on the closed interval from a to b. And the trichotomy principle, so f prime greater than 0, f prime less than 0, f prime equal to 0, although this just about never happens. If it's equal to 0 for all x in the open interval from a to b, then f is constant on the closed interval from a to b.
Really?
Yeah. Huh. The derivative is 0 all the time. All right. So let's find the intervals on which this polynomial function is increasing. Before we do this, I just want to say one thing that they used to do a lot of in textbooks is they would give you fairly ugly polynomials, have you take the derivative of it, factor the hideousness that they frequently were, and trying to find intervals where it was increasing and decreasing so that you could sketch the polynomial well. The advent of having a calculator that'll do that in, a very short span of time has made those problems basically obsolete. Although when you go to college, you may end up in a Cal 1 class where they spend time doing that because they're like, we don't do things with calculators here. I'm like, do you use toilet paper? They're both good inventions that have made our lives better. All right. So we'll take the derivative. I think everyone should have used a pine cone at some point. Is 3x squared minus 2. I got Lily and Brett.
You got Brett? That's pretty good.
Messed up my writing.
That was just so unexpected.
What about like a leaf maybe?
Yeah, I had a friend who was in the Boy Scouts who accidentally, there may have been some poison ivy mixed in there.
Oh.
Is equal to 0.
Yeah.
So we're going to find critical points.
Yeah.
So solving that, we're going to have 3x squared is equal to 2. So x squared is equal to 2/3. Remember that when you take the square root of something, we could always have a positive or a negative square root. Okay? Oh, thank you.
Hey, again, yes sir.
The square root.
Yeah, that's what I said.
Yes. Never mind. I'm just going to go on. So those are the only places where the derivative is equal to 0 because this is a continuous function. And so what we want to do, although a sign chart on a number line is not enough if they ask you to justify your answer, it certainly is helpful. They don't like you either. And you could test values, but this is a simple parabola, right? 3x squared minus 2.
It's Judy.
You know who that is?
The dog. Judy.
Is that the one that keeps coming onto campus over and over and over again?
Sounds like you
sits
beat
in my
with
parking
Judy.
spot.
I just have seen Tony with her.
I've almost ran it over a couple times.
So 3x squared minus 2, if this was the x-axis, the y-axis would be right through here, and the parabola is an upward-facing parabola, so it would be below the graph, above the graph, or excuse me, above the axis, then below the axis, and then above the axis, right? So on this interval, f prime is less than 0. On this interval, f prime greater than 0, and over here, f prime also greater than 0. If you are not certain, you can just substitute in some x value inside that interval into the derivative, not into the original, into the derivative to see what sign the derivative has. Okay? So where is this function increasing? Well, on the interval from negative infinity up to and including negative square root of 2/3. And starting at the square root of 2/3 to infinity. Again, if you were asked, sorry?
Why are negative 2/3 and positive 2, like square root included in it? If it's 0 at those points?
Right, but we don't care at that point,
Okay.
right? It's on the interval. So what's going to happen is it's going to increase up to that point, and then what's going to happen is your graph is going to start going back down. Or if it was going down, it'll go back up. Okay? All right. So, what we have just done is the first derivative test for critical points. Okay, usually just people say the first derivative test. And here's what we have. Let f be a differentiable function and c be a critical point of f. Notice in order to be a critical point, what are the two possibilities? No. To be a critical point.
Oh.
What's 0? The derivative is equal to 0, or what's the second possibility? Yeah, the derivative doesn't exist, but the function does. The function has to exist or you don't have a critical point there. Okay? If f prime of x changes from positive to negative at x equals c, then f of c is a local maximum. Think about that for just a second. If the derivative changes from positive to negative, when we have a positive derivative, the function is increasing. It's going to get to that point. Then f prime changes from positive to negative. Now, when f prime is negative, the function will be decreasing. So f of c is a local maximum. If f prime of x changes from negative to positive at x equals c, f of c is a local minimum. And if f prime of x does not change sign at x equals c, f of c is neither a local minimum or a local maximum. This gets tested pretty regularly on one where they ask you to justify your answer. And so you need to say things like this. And you have to be really careful about, sometimes they'll ask about global maximums and global minimums. Right? You use the candidates test for those. You use the first derivative test for critical points for local maximums and local minimums. One of the things that will absolutely get your answer nailed to a wall is making a local argument when they're asking about a global value or vice versa. They'll be like, oh, they don't know what they're talking about. And they go on to the next part. All right. So let's analyze the critical points of f of x equals x cubed minus 27x minus 20. And just for fun, we'll add on the phrase justifying your answers. So we'll take the derivative. And again, when you're taking the derivative, tell everyone that you're taking the derivative. Don't just take it and expect them to know, hey, you know what I mean. So 3x squared minus 27, we'll set that equal to 0. I think you can do that one pretty quickly in your head. X is equal to plus or minus 3. Okay, again, although having this by itself is not enough for a justification, having a number line is not a bad idea. Again, this one's not too bad because, again, it's just a simple quadratic, right? So in here, we know that f prime is going to be less than 0, f prime greater than 0, f prime greater than 0 over here as well. Okay? So the graph of f, I mean, you certainly don't need to draw it in, but the graph of f looks like that. Or it's graph of f prime, excuse me. So, at x equals 3, All right, let's do -3. Sorry, I'll go left to right. F has a local maximum because F prime changes from positive to negative at x equals -3. If you want to get super anal about it, although I don't think they have ever taken off for this, and I certainly don't, it would be f prime changes from positive to negative at x equals 3 as x is moving from left to right. Right? Because you could theoretically move right to left. And then at x equals 3, f has a local, what? Minimum. Because f prime changes from negative to positive at x equals 3. Everybody good on that? All right. Let's look at this next one. We'll do the same thing. So we'll take the derivative, f prime of x. It's going to be x squared minus 2x. We're going to set that equal to 0. So I'm going to factor out an x.
Isn't it x squared minus 2x plus 1?
Yes? I was just seeing if you were paying attention.
Oh yeah. Oh yeah.
Yeah, when was the last time you believed that when a teacher said it? So you were cynical even in 2nd grade?
Yeah.
Yeah.
I went to 2nd grade for like 2 weeks.
Life was tough then.
You're in 2nd grade for 2 weeks?
Yeah.
Don't ask questions.
He's like, alright,
He's just
cool.
like, okay.
So the only critical point is x is equal to 1. I'm just going on.
Yeah.
Is that the year that you skipped?
Yeah.
I can remember your parents being very concerned about that.
They shouldn't be.
I think he was too smart.
I stayed
I tried to assure them that you would be fine. I did.
I was.
How many grades could you have skipped?
7.
When I was at TCU yesterday, they told us a couple years ago they had a kid who went when he was 10 years old.
What?
And graduated
Yikes.
at 14.
That's it.
Why?
Man, it's like partying.
Yeah.
You just sighed.
So there's only one critical point here. It's that x is equal to 1.
Yeah.
Do you reckon? So that's x minus 1 quantity squared. That means that this was a double root, right?
Ah.
Yeah. All that stuff is still important.
Dang it.
And it's a positive x squared, so it looks like this.
20?
So
That was a really good collective sound effect that we all
Yeah,
just had.
f has neither a local maximum nor a local minimum. At x equals 1. And I might as well finish it, give the justification, because f prime does not change sign. at x equals 1. Okay, this is the case, we talked about it earlier when we were doing like velocity. Just because the velocity is 0, does that mean that the object changes directions? No, it could continue on the same direction. That's basically what this one is doing. It has positive velocity, the 0 velocity, and then positive velocity again. Okay? Page 3. Analyze the critical points and the increase/decrease behavior of f of x equals cosine squared x plus sine x on the open interval from 0 to pi. That'll give you the willies. So f prime of x, what's the derivative of 2 cosine x? See how sharp you are today.
2 cosine x times negative sine of x.
Yeah, 2 cosine x times negative sine x. Helps that I said part of it, doesn't it? Plus, the derivative of sine is cosine x. And we want that to be equal to 0. You might think this is one that you need a calculator for, but it is not.
Yes.
Because you can factor a cosine of x out of it. And I'll have negative 2 sine x plus 1. On the interval from 0 to pi, where is cosine of x equal to 0?
0 and pi.
Pi over 2. Wow, that was a group swing and miss. And then here we're going to have 1 minus 2 sine of x equals 0, which means that sine of x has got to be equal to a half. So x equals pi over what?
Pi over 4?
Not pi over 4.
What was
No,
that?
you're not 5 over 6.
Pi over 6?
Pi over 6 and
Turn that unit circle. It was like 3 pi or something.
well, that wouldn't be between 0 and pi.
Wow.
And sine is negative in the fourth quadrant, so that's 2 strikes. There we go. So x equals 5 pi over 6. So we've got all kinds of critical points going on here.
Yay.
So I'm going to do something from 0 to pi. Pi over 2 will be right in the middle. This will be pi over 6. And 5 pi over 6. And we have to analyze the sign of the derivative at some points in here. Well, between 0 and pi over 6, there's nothing really nice, is there? I'm going to skip it for now. Between pi over 6 and pi over 2, well, pi over 4 is nice. Yeah. So cosine would be square root of 2 over 2. I don't really care very much about its value. All I really care about is this factor going to be positive or negative? It's positive. Here I multiply, sine at pi over 4 is square root of 2 over 2. The 2's cancel. I get negative square root of 2, which is about negative 1.414. Plus 1 is negative.
0.4.
So that's going to be negative. So f prime negative. That was interesting. I literally wasn't touching it. If I do 3 pi over 4, well, cosine in the second quadrant is negative, so that's going to be negative. This value isn't going to change. It's still negative, so f prime greater than 0. Notice that this expression is going to change signs at the pi over 6 and the 5 pi over 6, the 1 minus 2 sine x. So, and the cosine is not. So this is going to be f prime less than 0, f prime greater than 0. So f is increasing on the interval from 0 to pi over 6. We don't include 0 because it wasn't part of our original interval. And then again on the closed interval from pi over 2 to 5 pi over 6. F is decreasing on the closed interval from pi over 6 to pi over 2. And the partially closed interval, the half close, from 5 pi over 6 to pi. Again, that bothers some people because they're like, well, how can I include pi over 6 in both of these intervals? Again, it's part of an interval. We're not saying that at pi over 6 it's increasing or decreasing. So then because I go from a derivative that's positive to a derivative that's negative, f has a local maximum at x is equal to pi over 6. And again at, what, 5 pi over 6? And f has a local minimum at x is equal to pi over 2. Okay? Any questions? Okay.